Hey, welcome back. So we've talked about hash functions a bunch now, and as in the lecture notes, mostly they're designed as a first step. You take a hash function for fixed length input, and then essentially you make this a hash function for arbitrary length input using Merkle-Darmstadt, for example. And this first step of coming up with a hash function for fixed length input, that's usually in practice for like SHA-2, for example. That's indeed like an art, a science. So you construct these kind of heuristically. You know what kinds of attacks are possible. You know what kind of properties you usually want from these hash functions. And then you just come up with the one that kind of throws around bits a lot. And for those hash functions that you design in practice, they are like really good. They're like SHA-2. There are not many successful attacks against them or anything. And they are really fast. They have a bunch of good properties. The thing is just we can't prove them secure, because that's usually not how they are like designed. Interestingly, there are some hash functions, however, that we can prove secure under some standard hardness assumption. And this tutorial will be about the hash function that we get from discrete logarithms. So this hash function works as follows. We first choose a group of prime order P and a generator G. And then what we're doing is we generate a bunch of group elements, random ones. And then the hash key S is just the group parameters and all of these HI. And then to hash, we just output the product of all of these HI to the power of Xi. And so this power operation and this multiplication here is the group operation. And the input to this hash function we expect to be values from ZP and many of them. So this is a fixed length hash function. If you take a little bit extra care, you can also make it work for bits. But let's just, for simplicity, assume these Xi are values in ZP. And now basically, this hash function, which is really easy, it is secure under the discrete logarithm assumption. So how does that work? As usual, we start with an adversary against this hash function, and then we come up with an adversary against the discrete logarithm assumption. The first thing that A prime needs to do, if it wants to run A, then A will want to see the hash key. So A prime needs to come up with a good hash key. And now the idea will be that A prime, its interest is in finding x given g of x. So finding the discrete logarithm of g of x. And so what it will do is it will sneak in this g to the x into one of these hi. And then choose out all of the other hi in a way that will later help us compute stuff. So we're guessing. So what we're doing is we smuggle in our g to the x as hj, and then we set all of the other hi to be just g to the yi for some yi's that we choose randomly. So then we give s with all of these values to a. So a then tries to output a hash collision like that. Now if this is actually a valid hash collision, then we will get that the hash value of these two pre-images is the same. And now in our special scenario where we chose all of the hi to be g to the yi and hj to be g to the x, we can now write this differently. We can basically plug in the values that we have for the hi. And now what you can notice is that all of this essentially is one big equation in the exponent modulo n over these yi, zi's, and x. Because g is a generator, so we can deduce that this is the case. And now basically we want to solve for x. So we get this by subtracting this and then subtracting this. And now we're just hoping that zj prime minus zj is not equal to 0. Because if it's equal to 0, then well, any information about x is just lost in all of this, and we can't do anything. However, if it's not equal to 0, then we get this equation and we can essentially compute x. Because we know all of the zi from the adversary, that's the hash collision that he's giving us. We know all of the yi, except for, let's say, yj, because that's our x, but that is not part of this sum. And so we can just compute x then. So essentially, if the collision that A outputs is such that zj prime is not equal to zj, then we can compute x. So what's the argument that this happens regularly? So what's the probability for this to happen? Yeah, similar to many of the other arguments that we had where we chose a random index, we're just hoping that something happens for that index. And the thing that we're hoping for here is that in this collision that the adversary outputs, we know that if this is supposed to be a valid collision, then z is not equal to z prime. So in particular, one of these zi need to be not equal to one of these zi prime. Because otherwise, if they're all equal, then this is not a collision. So what we're just hoping for is that there's at least one index that needs to exist for this collision is j. And so this happens with probability at least 1/n. So then we can do the whole analysis, and we will notice that if we guess correctly and the adversary wins, we can output x, the DLOG that we were looking for, and we are lucky with probability at least 1/n. So this works. And then, of course, if we believe the discrete logarithm assumption, then this adversary A prime that we're constructing should have negligible success probability. So also the success probability of A needs to be negligible. Okay, so this was the DLOG hash function, which is nice because it has nice properties and because we can actually prove something about it. Thanks for your attention and see you.